all, this is Mr. G, and this is our warm-up for today's lesson. Probably looks a little intimidating based on what we did in our previous video, but here's what I want you to do. I don't want you to answer this full question right now. All I want you to do is take this problem and read it through and then use that to fill in the information in this table. Right? That's the goal for this warm-up. Basically what we're doing is we're taking a actual linear programming word problem and turning it into something that looks like one of the charts we used in yesterday's video. So that's what I want you to do. Just fill in all of these spots with numbers, all right? And then after that, we're going to continue our linear programming process and actually solve this problem. But fill in the chart, then come back when you think you have that done. So we're going over 3, 2, 1, let's go. All right, so reading through the chart, you need to buy some, reading through the problem, excuse me, you need to buy some filing cabinets. You know that cabinet X costs $10 per unit, requires 6 square feet of floor space, and holds 8 cubic feet of files. Cabinet Y costs $20 per unit, requires 8 square feet of floor space, and holds 10 cubic feet of files. The office has room for no more than 72 square feet of cabinets. If you have been given $140 for this purchase, how many of each cabinet should you buy to maximize your storage volume? As soon as you see this word maximize, you just think, oh, this might be a linear programming problem. A problem where we need to sort of maximize something given the constraints, the limitations we're dealing with, and that's exactly what it is. All right, let's take a look. So cabinet X, the cost is $10, so hopefully you put $10 right there. The square feet, remember, you don't say feet squared, it's square feet, that's what that means right there. The square footage for cabinet X is 6 per cabinet, and it holds 8 cubic feet of files. So cubic feet, it holds 8 cubic feet of files. So that's the volume of those cabinets. Then cabinet Y, the cost is $20. The square feet is, or square footage, I should say, is 8, and it holds 10 cubic feet. So hopefully that's the chart you came up with. What we're going to do now is continue this process and complete the linear programming problem. So let's jump right in and get a little bit more space. All right, so there are some numbers we do not yet have in our chart, the 72 and the 140, and those are important because they're the limitations. Those are what give us the constraints. So let's put them right under the chart right here. Let's see, 72, that's a limitation on the square feet, and 140, that's a limitation on how much money we have to spend. So those are going to help us come up with our constraints. But before we do that, let's come up with our objective function. The objective function, remember, is an equation that represents the value we're trying to maximize. And if you read carefully, what we're trying to maximize is not money this time. We don't want to maximize the cost. We want to maximize how many files we can store. We want to maximize our storage volume, our storage space. So let's use an S for storage space, and let's see. We get 8 per cabinet X, so that's 8X, plus 10 per cabinet Y, 10Y. This is our objective function. So later, once we have our feasible region graph, this is the function. This is the equation we're going to jump back to figure out how we can get our maximum value. All right, but before we can get our feasible region, we need our constraints. So let's draw a line right here for our constraints. The first one, our cost is a constraint, or our cost is constrained, I should say. We can't just spend an infinite amount of money. We only have $140 to spend on these cabinets, which is actually not a lot of money. I guess these are cheap cabinets. All right, so let's take a look. So something's going to be less than or equal to 140. So it's going to be $10 per cabinet X plus $20 per cabinet Y has to be less than or equal to 140. 140. Now we know there's going to be a second constraint, our square footage, but before we do that, let's get this constraint done with. Let's solve for Y and put it into our graphing calculator just to make this process a little quicker. So we're going to subtract 10x, just getting Y by itself. We end up with 20Y is less than or equal to negative 10x. Again, I'm having trouble drawing my x's for some reason, plus 140. And then we divide everything by 20, distribute the division to the other side, and we get Y is less than or equal to negative 1/2 x plus, cross off the zeros, plus 7. Let's plug that right into our graphing calculator, turn it on. Let's go to Y equals before graph. It's negative 1/2 x plus 7. I'm going to leave that right there because we need Y2. We need our second constraint. So a little bit more space. Scroll back up. Let me see. So the other constraint we have not used yet is the 72. So that's a maximum amount of square footage there. So it's going to be 6x plus 8y, just getting that right from this column. 6x, so 6 square feet per x, plus 8 square feet per y has to be less than 72. So 6x plus 8y must be less than or equal to 72. Let me double check those numbers one more time. Let's draw a line here just to show that this is the second constraint. 6x 72, 6x 72. Excellent. Now we're just getting y by itself. Let's see. So we take away 6x. We should be good at this line now. We get 8y is less than or equal to negative 6x plus 72. Divide everything by 8. And let me see. That comes out to y is less than or equal to negative, divide both of those by 2 and get 3/4 x plus 9. 72 divided by 8, yeah, that's 9. Now let's plug it in. So it becomes negative 3 over 4 x plus 9. And then we hit our graph button. So we can see our feasible region. All right. Oh, we can't quite see all of it. Like we're sort of missing where it's crossing the real roots. Now there's a couple ways to, or where it's crossing the x-axis. We're missing the real roots is what I meant to say. We could hit the trace button and then just hit like right till we get there and it'll move the window. But I'm going to show you another way to do this. First, I'm going to zoom out and we'll zoom out. Let's see, we'll zoom out around here, sort of the middle of where a feasible region is going to be. Sometimes that'll give us a nice picture. It doesn't look like it does this time. So now we're going to zoom in, but we're not going to zoom back in on the same spot. We're not going to zoom in around the origin. I'm going to move my cursor and make sure it's in the middle of this feasible region. Hopefully you can see that cursor on the screen moving around left and right. I've got that in the middle of the feasible region and I hit enter. And this hopefully will give us a better picture. There we go. We can see our feasible region right there. Now, you might not need to do this, but I recommend, let me see if there's enough space up here. Yeah, there's space up here. I recommend drawing the feasible region, this four-sided shape, which is, or which represents all of the possibilities. And the reason I do that is because, one, it's tough to draw on the screen where the not where the smartboard is, but where the graphing calculator is. So hopefully this will help you see the points a little bit easier. But also it's just a good way to show your work because you know when you have a quiz, your teacher's not going to be able to see what you have on the graphing calculator. So being able to put this on pencil, putting it on paper will be an advantage. Okay, so now we've got to find these points. Let's start with this one. That is a y-intercept. So I'm going to hit second graph to look at the y-intercept. I'm going to make sure that x equals 0 is highlighted. It is. And it's either 7 or 9. Hopefully remember from our last video, we want the smaller one. So it can be 0, 7. Right. Remember, as long as we're shading below, which we always will be in this class, later it can get more complicated, but as long as we're shading below, we always want the smaller y-intercept. Now this point is the intersection of our two constraints. So I hit second, calculate 5 for intersect, go to the right. We're actually pretty close. So I can just hit enter, 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 since we only have two functions, and it's 8, 3. So 8, 3. And last but not least, we need this point, which is one of our real roots. I hit second, calculate 2 for 0, and then I move to the right. First, let me make sure I'm on the correct function. I am not, so I'm going to hit down to get to that other function. Let me move a little to the left, enter for left bound, move right till I pass the real root. Oh, that's, I don't know, the calculator's screwing up again. That's good enough. Okay, cool. So where was I? Right bound, hit enter, enter for guessing, and we get 12, 0. 12, 0. Right, now we've got our important points, because remember, like we learned in yesterday's video, the maximum or minimum value always comes from the vertices, or one of the vertices. I guess it could possibly be more, but if it's going to happen, it's going to happen at a vertex. So those are the points we need to check. Did I say if it's going? Well, there's always a maximum or minimum value, but we have to check the vertices, the corners. That's what it comes down to. I don't know why I'm stuttering so much. Let's see, what am I doing? So 0, 7, we're going to plug that right into our objective function. Let's check 0, 7 first. So 8 times 0 is just 0, plus 10 times 7 is 70. So this one gives us 70 cubic feet. Let's check 8, 3. 8 times 8 is 64. Do this up here. plus 3 times 10 is 30, and that becomes 94 cubic feet for that one. And now we check 12 zeros. So 12 times 8 is 96. Obviously, plus 0 just gives us 96 cubic feet. So that's going to be our maximum, 96 cubic feet. So what that means, to get the most storage space for the money we have to spend, to get our maximum amount of 96 cubic feet, we need to buy 12 cabinet X's and 0 cabinet Y's. That's what this means. All right. So a little bit of a warm-up, sort of mixed with an example here. Let's jump to our objective. So today we're doing chapter 3, section 4, and after today we should be able to use linear programming to find maximum values based on constraints. Same objective as our last video, because last video was really sort of a setup. Today we're going to attack our first real linear programming problem, which is we actually just did in the objective, or not the objective, in the warm-up. But let's do one more. Now, if you want to, you could try this one on your own, or like try different steps on your own. Feel free to pause the video at any time. I'm just going to start running through this problem, ironically, running.com, see what I did there. And then whenever you want to try and move ahead or check your work, feel free to pause, unpause the video, but I'm just going to start working. Let's go. First, let's read it. It says running.com is a company that manufactures and sells shoes. Two types of shoes they sell are the Bolt and the Lewis. The Bolt takes 1.5 hours to assemble and 0.25 hours to test. The Lewis takes 1 hour to assemble and 0.5 hours to test. Each day, running.com has 12 available hours for product assembly and 4 hours for product testing. Running.com earns $15 profit from each Bolt sold and $18 profit from each Lewis sold. How many of each type of shoe should running.com produce to obtain the greatest profit possible? Now, I know these are sort of simplistic numbers, but we're doing sort of simple linear programming problems. Obviously, the numbers are going to get a lot more complex, and there will be more constraints in the real world, but we're just sort of getting used to this process. Now, the first thing I always like to do is make a chart. And that's pretty much true for any word problem I do. When I see a paragraph, my eyes sort of roll into the back of my head. But if I can create a chart, that makes it a lot easier for me to figure out what we're looking at. So really, we're comparing two things. We're comparing the two types of shoes. One is the Bolt, which will make X, and the other was the Lewis, which will make Y. It doesn't matter which one's X and which one's Y. I just pick those. Usually I make the one I see first X. Now, what are they giving us about these? So they're talking about assembly time and test time. So we're comparing, okay, we're not comparing. We've got different times for assembly. I have to be careful how I abbreviate that word. And different times for testing. All right, and the other information they're giving is profit. So we've got different sort of profit values for these two shoes. Now we just fill in the numbers. So for the Bolt, it says 1.5 hours assembly and 0.25 hours to test. Then we've got the Lewis, which takes, where is it? Takes 1 hour to assemble, so it takes less time to assemble, but 0.5 hours to test, so it takes longer to test. And then the profits for a Bolt are $18 profit per pair of shoe. And, oh, no, the 18 was for the Lewis. And let me scroll up and read this carefully. I don't want to screw this up. Earns $15 for each Bolt. Yeah, so we put 15 there. And 18 profit for each Lewis sold. Okay, good. I feel like we're missing some numbers. Yeah, we don't have our constraints yet. We don't have our limitations. So it says each day running.com has 12 available hours for production. Wait. Available for product assembly. I read that incorrectly. So assembly, they've got a maximum of 12 hours. And for testing, they've got a maximum of 4 hours. So this is what our chart looks like. Now, once we have the chart, we can go straight to our objective function, constraints, feasible region. Hopefully, it all just starts rolling from here. So let me see. Let's start with our objective function. Now, remember, the objective function is all about what we're trying to maximize. Here, we're trying to maximize the profit. We're trying to find the greatest profit possible. So that means we look at this column right here, the 15 and the 18. So that would be the profit is going to equal 15 times X plus 18 times Y. That's our objective function. So we're going to come back to this at the very end to figure out which one of our vertices, which one of our corners maximizes that profit. Now we need our constraints. So constraint 1 Let's use the 12. So that means we're using this column right here, the 1.51 and the 12. The 12 is the maximum amount of time we can spend assembling these shoes. So let's see, it's 1.5 per x plus 1 per y, which I guess we could just write that as y. That's probably acceptable. That's easier. That's less than or equal to 12. So now all we do is we get y by itself. So I'm going to take away 1.5x from both sides, and that's all we have to do. We get y is less than or equal to negative 1.5x plus 12. Now we just need the graph. I go y equals, oh, gotta turn it on. Y equals, let me clear the old ones out. Clear. Go back up, and it's negative 1.5x plus 12. Graph it? Oh no, let's wait to graph because we have a second constraint. What am I doing? So the second constraint has to do with the amount of testing time. This column right here. So it's going to be 0.25 per x plus 0.5, so 0.25 per x. You draw a line to separate them. Plus, what was it, 0.5 per y? Yeah. Must be less than or equal to 4. Now we just get y by itself. Take away a quarter x, take away 0.25x from both sides. We end up with 0.5y is less than or equal to negative 0.25x plus 4. Then we could divide both sides by 0.5, but I'm just going to multiply by 2 because we're trying to get that to be a 1y, and I think that's easier. Now, if you want to divide by 0.5, you can do that in a calculator. That's fine. But I think it's going to be easier to sort of double that, because 2 times 0.5 gets us to the 1y we're looking for. So I double the negative 0.25 and get negative 0.5x plus double the 4 and we get 8. Right to y equals, go to y2. That's negative 0.5x plus 8. Hit graph. Let's see what our feasible region looks like. Oh, we messed up or we messed with our window, but it looks like this should still be fine. Yeah, we can still see it fine. So now let's go to our feasible region. Let's scroll up. Let's see if we have space. Yeah, we should be able to fit it right here. So the feasible region looks like this. You don't have to draw it, but I think it's a little bit easier. It helps me keep my work organized. So I'm going to draw that. Let's get a little bit more space. Whoa, what happened there? Try that again. Smartboard's getting a little jumpy. There we go. All right, now let's find our vertices. That's the y-intercept. We hit second table, pick the smaller one, so it's 0, 8. 0, 8. I actually don't like how crammed this is getting. Let's draw a line to sort of separate this. And now we find this point, which is our intersection. Second, calculate 5. We're actually pretty close. Enter, enter, enter. 4, 6. 4, 6. And that doesn't look like a 6. Let's try that one more time. That's a little better. And then we find our third and final point, which is our real root. Second, calculate 2 for 0. And I actually am on the right function this time. That's nice. I'm going to hit enter. Left down, move to the right, hit enter. Enter again. And we get 8, 0. Not sure if you heard that, but we got some like construction going on in the hallway. Hopefully we'll get through this before they have to come in here. All right, now real quick, we're just going to take those vertices, plug them into the objective function, and see which one gives us our maximum value. So 0 and 8, that's 0 plus 8 times 18 is 80 and 64. That's 144. So we get 144 for that one. Next, we plug in 4, 6. 4 times 15 is 60. Plus 6 times 18, that's going to be 60. And 48, that's 108. So this one comes out to $168. And last, we plug in 8, 0. 15 times 8, that's 80. And 40, that's 120. Plus 0, obviously. And we get 120. So our maximum value is 168 with the point 46. 46. Now, let's put that in context. So that means they should make 4 pairs of bolts and 6 pairs of Lewis's. Now, obviously, we know these are very simple numbers. If this was a real running company, they'd have to make a lot more than just 4 of one pair and 6 of the other. But we're sort of just getting used to this process and seeing how it could apply to the real world. All right, that was our lesson for today. If you have any questions, by all means, reach out to me. Otherwise, enjoy the rest of your day.